Good evening, sir.
Good evening, madam.
Will you start, sir?
Yeah,
Yes, sir. Good evening to everyone. We are assembled here for the online international workshop on statistics using Jamovi. So we have with us our resource person, Dr. R.D. Chaudhary, sir, Associate Professor of Statistics, MG Science Institute, Ahmedabad, Gujarat. Welcome you, sir, for the session.
thank you, madam.
Yes, sir. Please, sir. Thank you, sir.
Okay. Okay, good evening, all. Today's good evening, all. Today's session is about the analysis of variance, which is again a very important topic for the statistical analysis. 1 minute. Just a minute. Okay, so today's session is about the analysis of variance, which is a very important topic. Yesterday, Parag sir explained you about the parametric test and the non-parametric test. So in the parametric test, we have one sample t-test. Then we have two sample t-test. In two sample t-test, we have independent sample t-test and dependent sample t-test. So the t-tests are basically used for one or two sample. But when we have to compare more than two populations, when we have to draw some conclusion about more than two populations or the homogeneity of the more than two populations, then we have the generalization of the t-test, and that is the analysis of variance. So in the analysis of variance, we will discuss about what is analysis of variance, and there are basically different ANOVA techniques. One is one-way ANOVA, we have two-way ANOVA, and in general we have n-way ANOVA also. And then there are some design of experiment topics, so that we are not going to cover, but we will discuss about one-way ANOVA, some theory behind the one-way ANOVA, and then when we are comparing more than two groups, more than two populations or samples. So obviously, in that case, we have to go for the pairwise comparison. That type of analysis is known as a post hoc analysis. So in the post hoc analysis, we will compare all possible pairs for the significant difference. This is about the theory of one-way ANOVA, and then we will discuss with the help of some example how to carry out one-way analysis of variance using Jamovi. So basically, in the statistical techniques, almost all the statistical techniques, majority of the statistical techniques has some number of assumptions. So we have to check the assumption for each of the statistical technique, and depending upon the validity of the assumption, whether they are satisfied or not, we have different statistical methods, right? So we will see that with the help of example, and then we will perform post hoc analysis or post hoc comparison in Jamovi. This is about the parametric analysis of variance. Now, if the assumptions of the analysis of variance technique, they are not satisfied, then we have a non-parametric analysis of variance technique, that is non-parametric counterpart, that is the Kruskal-Wallis test. So we will discuss one example using Kruskal-Wallis test, how to carry out, how to perform Kruskal-Wallis test in Jamovi, right? So first of all, the question is, what is analysis of variance, right? So this is a very important question because we know that in t-test we compare one group, two groups, dependent or independent. So in the analysis of variance, it is a procedure for testing the difference among different groups, or in short, when we say more than two groups of data for the homogeneity. That means whether the more than two samples are coming from the same population or different population. So that we want to compare. So in short, in a very simple way, it is used for testing the difference, significant differences between two or more means. So basically for two means, we have already a t-test, independent sample t-test or dependent sample t-test. But when we have to compare more than two means, then we can go for analysis of variance, right? Now, the most important question, that is, actually we are testing the mean of more than two groups. So we are testing means of more than two groups, but the technique is known as analysis of variance. So the reason is, because we are comparing difference between the group means by analyzing the difference between the group variances. So in short, we are analyzing the variation. We are analyzing the variabilities, right? Variances to compare means. So that is why it is known as an analysis of variance technique and not analysis of mean, right? So the technique it is given by Professor R. A. Fisher, Ronald A. Fisher. According to Professor R. A. Fisher, ANOVA is nothing but the separation of the variance due to one group of causes from the variance due to another group of causes. So if we collect the data, so there is some kind of variations in the data, right? So according to Professor R. A. Fisher, we are separating the variability. How much variability is due to some causes and how much is due to other causes. So that is the definition of analysis of variance. So if we check any data, if you take any data, so in that entire data, there is a total amount of variation that is known as a total variation or total sum of square, right? And that variation is broken down into component variation. So what some amount of variation is due to specific causes, that is known as assignable causes, because experimenter is applying different treatment. So there might be some variations, that is known as variation due to specific causes or assignable causes, that can be detected or can be controlled because experimenter is applying different treatment, right? But some amount of variation is a random variation, that is known as a chance variation, right? So in short, in analysis of variance, our purpose is to analyze the total variation in the data. We split the total variation in the data into two components. One is due to assignable causes and another is due to the chance causes. So in short, the earlier statement which we have discussed, instead of analysis of means, it is known as analysis of variance. That means for comparing more than two group means, we are analyzing the variation. That is why it is known as analysis of variance, right? So this is a very simple example I have taken. So that is the dissolution of tablet is compared for three experimental batches. So I have three experimental batches and the same kind of tablet, right? So the three experimental batches, and with respect for each point is the time in minutes for 50% dissolution of a single tablet. So the first batch, right? So some number of tablets are taken and their dissolution time, 50% dissolution time for a single tablet. Say for example, for the first tablet, from the first batch, it requires 15 minutes to dissolve 50%. Okay, so this is the total data. Now, if we forget about the batch labels, so in all, we have total number of some observations. So if you look at the total data, okay, if you look at the total data, there is some kind of variation. If we remove the batch label, so we have total number of observations, right? All the observation combined together. So that variation or variance is known as the total variation in the data, right? So if you look at the data point, so all the data point, that means there is some kind of variation in the data. So that variation is known as a total variation, right? But if you look at the first row only for batch one, even though all the tablets are selected from batch one, still there is a variation in the dissolution time. If you look at the second batch data, all the four tablets are taken from second batch, still there is a variation, right? So if you look at batch one, batch two, batch three, so we can see that there is a variation. So obviously, when you can think that there is a variation in dissolution time because we have selected the data from batches. So because of batch, there is a variation, right? So that is known as a assignable causes. Because we have selected tablets from different batches, there is a variation. So that is the variation due to assignable causes, right? So instead of batch one, suppose the experimenter is applying some kind of treatment, right? So in that case, we have treatment one, treatment two, treatment three, right? So accordingly, we have the variation because of different treatment, right? So the total variation in the data, right? So within the batch, if you look at only batch one, so 15, 18, 19, 21, so there is an inherent variation. That is, same batch we have selected, but still there is a variation, that is a random variation. But if you look at from batch 1 to batch 2, there is a variation. Batch 1 to batch 3, there is a variation. From 2 to 3, there is a variation. That is the variation due to assignable causes. So in short, ANOVA is nothing but it is used for comparing means by analyzing the variances, right? So the research question for this particular problem is there a significant difference among the batches with respect to the 50% dissolution time? We mean 50% dissolution time, average 50% dissolution time. Okay, so this is the same thing. Now, when to use one-way ANOVA? So if you look at the data, what are the observations? So all these observations are nothing but the 50% dissolution time in minutes. All the observations combined together. So this is one variable, that is 50% dissolution time in minutes. That is a continuous variable or scale variable. So that variable is dependent. So dissolution time depends on the batch from which the tablets are selected. So the second variable is the independent variable, that is the experimental batch, right? So if you look at the data, 50% dissolution time, so it is classified with respect to one criteria, and that criteria is batch, right? So according to batch, we classify the dissolution time. So one criteria of classification, so such a data is known as one-way classified data. If we classify the data with respect to two different criteria, then we have a two-way classified data, right? So this is the example of one-way classified data. So in one-way classification, one-way ANOVA, we have one dependent variable, which is always a scale variable. In our example, it is 50% dissolution time in minutes. That is the dependent variable, and that depends on the batch. So batch 1, batch 2, batch 3. So experimental batch is our independent variable. Okay, so as explained earlier, so the basic principle of analysis of variance is to test for the difference among mean by examining the amount of variation within each of the samples corresponding to the total amount of variation. So in short, total variation is classified into variation. It is classified into variation uh, due to assignable causes, which is also known as a between variation, right? Between variation, and variation due to chance causes, that is within variation, right? Because from batch 1 to batch 2, there is a variation. So obviously, we may think that because of different batch, there is a variation. So between variation, okay, and within variation. That means if you look at the data for same batch, so same batch and different tablets are selected. So within that batch, there is a variation. So that is the chance variation, which is also known as the error variation, right? So this is the basic principle behind the analysis of variance, right? So to understand this, total variation in the entire data is variation due to specific cause. In our example, different experimental batch of tablets, right? So because the tablets are selected from different batches, there is a variation. Okay. And another is random variation, that is also known as a chance variation. So this is the main logic behind the analysis of variance, right? Now, what is one-way ANOVA? So it is nothing but an extension of independent sample t-test, right? So in independent sample t-test, we compare two groups, right? Two groups are independently, two samples are independently selected, and we want to compare the means of two groups, right? So in this case, it is an extension of independent sample t-test. That means when we have to compare more than two groups, then we can go for ANOVA, right? And when to use ANOVA? So when we have a categorical independent variable, which is also known as a treatment, right? With more than two categories, right? So for example, in our example, we have different batches. So this is my treatment. So with more than two levels, batch 1, batch 2, batch 3, right? If we have only batch 1 and batch 2, we can go for independent sample t-test. So basically, ANOVA is used when we have to compare more than two groups. Okay. So we have independent categorical variable and a normally distributed dependent variable, which is either interval or ratio. In general, we call it as a continuous variable or a scale variable, right? So that is known as a response variable, right? And when, what is the purpose? It is used to examine the difference between means of more than two independent samples. For more than two independent sample, if you want to check whether there is any significant difference between the means, so we can go for ANOVA, right? So this is how we can use the analysis of variance technique, right? So this is again the same thing. With respect to our example, we have one dependent variable, that is 50% dissolution time in minutes, and we have one independent variable, that is either nominal or ordinal with more than two levels. In our example, it is three different batches, batch 1, batch 2, and batch 3, right? Now this is just for your reference. I am not going into the detail. The reason is it is quite mathematical, but if you want to use this model in your research, so you can refer the corresponding books, reference books, right? So this is a mathematical model. So Yij is the observed value, observation, right? Say for example, it is a jth observation from ith treatment, right? And what is I? 1 to K. In our example, we have three treatments, batch 1, batch 2, batch 3. So my K is 3 and J, that is 1 to up to Ni. So there may be possibility that in each group, we have different number of observations. Like in our case, in one case, we have 5 observations. In another case, we have 4 observations, like that. Okay. So this is the mathematical model. This is just for your reference. Okay, so this is the mathematical model. So observed value is because of the effect due to factor, like in our case, because of the batches, there is a difference in the observed value, right? And the remaining part is the error part, that is EIJ, that is error effect due to chance, right? And mu, that is the overall effect, right? So this is a mathematical model for one way ANOVA, and this is just for your reference, right? Now the most important part is the assumptions, right? In independent sample t-test also we have some assumptions. So here also there are some assumptions. So these are the assumptions which are very, very important. If the assumptions are not satisfied, so we have to look for the different statistical method, or we have to look for the non-parametric method, right? So EIJ, that is error term, it is normally distributed. It is normally distributed. Or in general, we can say that observations are normally distributed. So your data is coming from a normal population. So that is the assumption. Okay. Errors have mean zero. So the average error is zero. So that is the assumption, right? And errors are independently distributed. In short, the sample observations are independently selected, right? And the most important, errors have equal variances among the factor level, right? So homogeneity must be there for the comparison of means, homogeneity in terms of the variances. So these are the assumptions, right? And the hypothesis, right? So you can write the hypothesis in terms of the alphas, that is the effect, or you can write in terms of the mean effect, right? So for example, in our case, it is mu1 equal to mu2 equal to mu3. So average 50% dissolution time for all the three batches are same against at least one pair of mu differ significantly, right? So this is this is the assumption, sorry, hypothesis which we want to test, right? And then according to the theory of one-way ANOVA, as I have already explained you, the total variation in the entire data is because of variation between the groups or variation within the groups. So between the groups is known as sum of square due to groups, and within the groups it is known as sum of square due to error. So in short, according to the Professor R.A. Fisher, total variation is classified into two components. One is due to one group of cause, another is due to other group. So it is SSG is due to assignable causes, SSE that is due to chance variation or random factor. And these are the formulae to calculate the sum of squares, right? But when we are using software, so directly we get the result. Okay, so this is about the theory of one-way ANOVA, right? And these are the notations which I have used in the formula. This is just for the reference. Okay. Then we have test statistics. Now for testing the hypothesis H0 against H1, right? So we calculate mean sum of square due to group divided by mean sum of square due to error. So that gives you the F test statistics. So for analysis of variance technique, F test is used. So ANOVA is not a test. It is ANOVA is a technique and the test is F test. Okay. And it follows F distribution with K minus 1, comma N minus K degrees of freedom, where K is the number of groups, N is total number of observations, overall all observations, right? So once we get the value of the test statistic, just like in T test, we get the value of T statistics. So here we get F statistics. Okay. And then we can prepare the ANOVA table. So this is the ANOVA table, right? So source of variation. So we have total variation, then variation that is due to groups, then error variation, their degrees of freedom, then their sum of square, which already we have mentioned here. So these are the sum of square, right? And this sum of square divided by the corresponding degrees of freedom. Say for example, SSG divided by K minus 1, it gives me mean sum of square due to groups. Similarly for SSE, and the F observed is the ratio of these two sum of square, right? And then we calculate the p value, and then depending upon the p value, we can take the decision about rejection of the null hypothesis or fail to reject the null hypothesis, right? So this is the approach, p-value approach, right? So if p-value is greater than alpha, which is the desired level of significance, 0.05 or 0.01. If it is greater than alpha, fail to reject the null hypothesis at alpha level of significance. Otherwise, reject the null hypothesis. Right? So this part is common for almost all statistical tests based upon the p-value. Right? Now, this is how we can represent the p-value graphically, right? So f test. So this is the graph of f distribution, which is always a positively skewed. Okay. So this is your f observed value. This is the f observed value, right? And below that, we have whatever the area, that is the p-value, right? So it is nothing but the probability that the f value is greater than the observed test statistic. So that gives you the p-value. Okay. Then comes, now suppose in this case, in any ANOVA example, right? Suppose we reject the null hypothesis, second part, p-value is less or equal to alpha. So when we reject the null hypothesis, what is our null hypothesis? Our null hypothesis is, our null hypothesis is all the means are equal. All the means are equal. So that is rejected. So if H0 is rejected, means H1 is accepted. So at least one pair of mu differs significantly. So it may be mu1, mu2, or mu1, mu3, or mu2, mu3. So that is why we have to go for a pairwise comparison. But remember, pairwise comparison is valid only if we reject the null hypothesis of ANOVA, right? So if you arrive at the second step, right? So p-value is less or equal to alpha. So reject the null hypothesis, then we go for the pairwise comparison, right? Now, what is the pairwise comparison? It is also known as a post hoc analysis, right? So we say that there is a significant difference, but particularly in which pair there is a significant difference. So we try to analyze further, right? So in three groups there is a significant difference, but particularly which two groups differ significantly. So for that we have to go for the pairwise comparison, which is known as a post hoc analysis, right? So there are different post hoc analysis, right? One is the Fisher's LSD, that is known as the least significant difference. Another is Tuckey's HSD, that is known as the honest significant difference. And next one, that is Dunnett's method. And this Dunnett's method is basically used when we are comparing some treatments with a control group, like placebo group, right? One group without any treatment, another group with say treatment 1, third group with say treatment 2, and then we are comparing. So one group is without any treatment, that group is known as control group, right? So when we are using this technique, when we have control group, then always go for Dunnett's method for the pairwise comparison. Otherwise, we can go for Tuckey HSD or Fisher LSD. But basically, in almost all research articles, the Tuckey's HSD method is commonly used, right? So pairwise comparison or post hoc analysis is applicable only if we reject the null hypothesis about equality of means for more than two groups, right? Then we can go for the post hoc analysis, right? So these are the formulas. Again, I'm not going into the detailed theory, but just for your reference. So this is the Tuckey's method. So once the null hypothesis is rejected, then one might be interested in comparing the pair. Suppose I am interested in comparing ith group and jth group. So mean for the ith group is same as mean for the jth group. Again, they differ significantly, right? So we can take I and j, I not equal to j, and different values of I and J. In our example, batch that dissolution time example, we can take I equal to 1, J equal to 2, that is 1, 2, then 1, 3, and 2, 3, right? And this is the formula, right? But directly in software, we get the test statistic, we get the p-value, and directly we can interpret, right? So this is all about the theory of analysis of variance for one-way classified data. Now the problem is how to analyze the data in Jamovi, right? Now remember one thing, in Jamovi, say for example, in our example, if you look at the data, so this is my data, okay? So if you look at the data, right? So basically how many variables are there? There are only two variables. One is a dependent variable, which is continuous, okay? Another is independent variable, that is experimental batch, okay? So remember, whenever we have this type of tabulated data, so never ever enter the data in this fashion in Excel or CSV or in any statistical software, right? Statistical software always require the data in such a way that columns are the variables, rows are the observations, right? So if you look at this, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So I have 15 observations. So I have to enter the data 15 rows, all the observations in a single column, because see, all these values are related to this label, 50% dissolution time in minutes, right? So all these 15 are the observation, right? And what are the variables? First variable is dissolution time. Second variable is experimental batch. Dissolution time is a continuous variable. Experimental batch, that is batch 1, batch 2, batch 3, is a categorical variable. It may be nominal or it may be ordinal, right? So this is a very, very important step, right? So usually what happens? So we may think that there are three columns. So we enter the data like this, right? So this data, even in SPSS or Jamovi or in any other, right? So this data is not allowed. We have to enter the data depending upon the number of variables. Okay, so let us move to the Jamovi part. Okay, so already I have this file, that dissolution.csv file, right? Dissolution.csv file. So let us open the file in Jamovi, right? So this is the data file, then menu, then open, right? And then go to the corresponding folder. And this is my CSV file, dissolution.csv. Once you open that file, you can see that there are two variables and 15 observations. Look at this, from 1 to 15, right? So 15 observations and two variables. The first column is the scale. You can interchange the order, right? It may be batch first and time second, that doesn't matter. But two column, one column that is a continuous variable, another column that is a categorical, right? So but since my data is in CSV format, right? So when we open the data file, many times it is not directly taking that as a continuous variable. So you can change that on double clicking that particular column. So you can change the data type to continuous. Okay, so you can change and you can add here, say 50% dissolution time as a description. Okay, same way you can add this batch, that is simply batch, right? And it is already a nominal type data, right? It is already a nominal type data. Okay, so this is my data, right? Now once we have the data, right? Now what is the problem here? Is there a significant difference among the batches with respect to the 50% dissolution time? Our question is the mean 50% dissolution time is same or different for the batches? So that we want to compare. And if there is a significant difference, then which batch is different, right? So that we want to compare, right? So this is how we can open the data file, right? And then we can just change the labels, data editing part. Okay, you can change the labels, and once the data is ready, now the first part, before applying any statistical method, first part is always understanding the data, that is exploring the data. Okay, so just go to analysis tab, exploration and descriptive statistics, right? So analysis, then exploration, descriptive, and then select the variable, right? So this is my continuous variable. So select it as a variable and split by batches. So we can have the detailed descriptive statistics, right? We can have a detailed descriptive statistics, right? So average dissolution time for batch 1, batch 2, batch 3, number of observations in each batch, right? If there are any missing values, so that will be indicated here. Their medians are also in the output. Standard deviation, that means variation in batch 1, variation in batch 2, variation in batch 3, right? Minimum value, maximum value. Apart from this, if you want more statistics, so you can choose from this, right? Say for example IQR or variance, right? So you can choose that. Even if you want the percentile, right? So you can choose that, right? So here, so these are the outputs, right? In the same summary table, we will get the output, right? So this is as per our requirement. We can use from the statistics section, we can select a different statistics. Okay, so this is how we can select, right? So as per the requirement, even as we know that we want to check the normality also, right? So to check the normality, we have to use the Shapiro-Wilk test, right? So again, as I told you, compared to SPSS, why Jamovi is more user friendly? Because already I have carried out the analysis. Okay, already we have carried out the analysis, right? Now suppose I want to uh, change some part from this, so you can edit that, right? And you can choose some additional options. So look at this. So these are the p values for the Shapiro-Wilk test. These are the p values for batch 1, batch 2, batch 3. Okay, so in that sense, Jamovi is uh, powerful than uh, SPSS, right? So this is how we can get the summary, right? Apart from that, again, same summary table, just scroll down and we have a plot section. In the plot section, either you can go for the density plot, histogram, right? Say for example, density plot. So look at this. So we will have a density plot, right? We will have a density plot for batch 1, batch 2, batch 3, or we can have a box plot. So these are the box plot, comparative box plot. So you can see, right? So these are the comparative box plot for all the 3 batches, right? So depending upon your requirement, you can choose that, right? So depending upon the requirement, even you can choose this QQ plot also, right? You can choose the QQ plot also, which is for the normality of the data, right? So this is the QQ plot, which is for the normality of the data. Look at this. So this is for batch 1, this is for batch 2, batch 3, right? So since we have limited number of observations, right? So it shows only few observations because the data is small. Okay. So, but this shows that almost all the observations for every batch, they are close to the reference line. So so we assume that the data is coming from a normally distributed population. Okay. Data is coming from a normally distributed population, right? So this is how we can go for, right? Now the next part, that is about the hypothesis, right? So since we have 3 batches, so mu1, mu2, mu3 are the mean dissolution time for batch 1, batch 2, batch 3 respectively, right? And then we have the hypothesis, null hypothesis, H naught, all the means are equal against. Now remember, when you are comparing more than two means or more than two variances, so never ever write the alternative that mu1 not equal to mu2, not equal to mu3, not equal to, right? Because it is not possible, right? So at least one pair differ. It may be possible that mu1 and mu2 are same, but mu1 and mu3 are different, or mu2 and mu3 are different, right? So that is why the alternative is always at least one pair differ significantly. Okay, so this is how we can set up the null hypothesis about the for one-way ANOVA data, right? Now, once we have set up the null hypothesis, once we have verified the normality, right? Still some other assumptions are there, and that other assumptions we have to check. Okay, so we have to go for the analysis of variance, right? Now remember, here in the analysis tab, we have the third on the ribbon, we have the third icon, that is ANOVA, right? Now look at this. So the icons are also user friendly as compared to SPSS. So for t-test, it shows only two. That means it is used for up to two. ANOVA, so it is more than two. Regression, so point, scatter plot, and a regression line frequency, right? So that is why it is user friendly as compared to SPSS, right? So go to ANOVA and we have one-way ANOVA. Okay, we have one-way ANOVA. If we have two-way ANOVA, if your data is classified with respect to two criteria, you can go for the general analysis of variance. Okay, then if we have analysis of covariance, some other variable is also there, then we can go for analysis of covariance. Okay, okay, we can go for analysis of covariance also, right? So these are different ANOVA techniques, right? After that, we have a non-parametric section, right? That is one-way ANOVA, and we have repeated measure ANOVA, right? So currently we are discussing the one-way ANOVA. So go to one-way ANOVA, and then we have a separate output, right? So this is one-way ANOVA, right? So once you select the data, once you select the variable, automatically we will get the result, right? So then let us take time, that is the dependent variable or dissolution time, batches, that is your grouping variable, right? So this is my analysis of variance, right? So by default, right? Remember, again, this is very, very important. By default, Jamovi gives you a Welch analysis of variance, right? So there are two ANOVA techniques. One is uh, Welch analysis of variance. Another is Fisher's analysis of variance. Now, what is the difference? The difference is on the depending upon the assumptions, validity of the assumptions, right? But here, if you look at below this, just to the extreme left, right? So variances, right? So here we have another option. Just tick mark that. So we have both the ANOVAs are there, Welch as well as Fisher's. And here it is mentioned, right? So if the variances are not equal, go for Welch ANOVA. If the variances are equal, if we assume that the variances are equal, then go for Fisher's ANOVA, right? So this is the analysis of variance table. Okay, so look at this. This is how we get the analysis of variance table, right? So once you select Fisher, you get both output. Okay, now what is the difference? So same already I have explained you, right? So Welch ANOVA is used when the assumption of homogeneity of variances is violated, right? That means when the variances are unequal for the batches, right? So the variability for batch 1, batch 2, and batch 3, if they are not same, go for Welch. If the variabilities are approximately equal, go for Fisher-ANOVA, right? So Jamovi gives you both output, but it is your duty, your role to choose which one is suitable depending upon the assumption, right? Then we have some additional statistics, right? So here these are the additional statistics. So select the descriptive table. So it gives you a descriptive table for dissolution time according to different batches. Okay, number of observations, their mean, their standard deviation, and their standard error. Okay, so this is the descriptive summary. If you want plot also, you can get a descriptive plot, right? So this plot is nothing but the 95% confidence interval. So the center point is the mean, right? So average dissolution time for batch 1, this is for batch 2, this is for batch 3, right? And these limits, lower and upper limit. So these are the 95% confidence limit interval. Okay, so these are the additional statistics, right? So this is how we get the additional statistics. Now the next part is assumption check, right? Now this type of assumption check is not there in SPSS, so we have to do it separately. So here it comes under the analysis of variance menu itself, right? So what are the assumptions, right? Homogeneity of the variances, right? So look at this. Already we have mentioned in our assumption, right? So if you look at the assumption, so already we have discussed that, see, observations, errors are independently distributed, errors are normally distributed. So we have to check the normality, right? We have to check the uh, equality of variances. That means homogeneity of the variances, right? So these assumptions we have to check. Okay. So it is already there in the menu, right? So look at this assumption check, right? Now see, for the assumptions, we have this test, right? So homogeneity test. So this is the homogeneity test. Now, what is that actually homogeneity test? So look at this. We have uh, two tests are here, outputs. One is a Leibniz test, another is a Bartlett test. Okay. So, and the title is homogeneity of variances, right? So both the tests are applicable, right? So Leibniz test, if in your case, if these tests are not appearing when you click on the homogeneity test, right? So because these are these tests are available under the more test module. If you go to module, right? So these are available under the more test module, right? So just let me show you that. See, these are the more test, right? So additional, say for example, Bartlett test, homogeneity of the variances. So by default, it gives you only Leibniz test. Okay, so for Bartlett test, you need to install this more test model. Okay, so in my case, it is already installed, so it is showing both the outputs. Okay, so homogeneity of the variances. So actually, what is the hypothesis for homogeneity? Variances in dissolution time for three batches are equal against at least two variances differ significantly. At least two variances differ significantly, right? Now, in this case, so the last column is the p-value that we want to compare, right? But before we check the p-value, right? So this is the output for the Leibniz test, F test statistics. Look at this. This is F test value 0.37 and the corresponding p-value 0.69. So which is not less than 5%. So we fail to reject the null hypothesis. That means variances are equal for three batches, right? So now same conclusion we can draw from the Bartlett test also. Okay, here also the p-value is 0.992, which is not less than 5%. So fail to reject, so variances are equal, right? Now we know that if the variances are equal, we have to go for Fisher-ANOVA. right? So if the variances are not equal, we have to go for the Welch analysis of variance technique, right? So that is one part. Okay. Now the next part is testing the normality, right? So this is about testing the normality, right? So once you click on that, we have the output, right? So here also we have Shapiro-Wilk test, we have Kolmogorov-Smirnov test, we have Anderson-Darling test. So these are additional tests for testing the normality of the data. Whether your data is normally distributed or not, that can be tested using all these tests. There are some advantages and disadvantages of this method, right? But commonly used is a Shapiro-Wilk test, right? And as I told you, because I have installed more test package module, so it gives me all. Okay, so these are the normality test. The last column is the p-value. Again, if you check, all the p-values are not less than 5%. Okay, so we can say that the data, the resolution time follows a normal distribution, right? The resolution time follows a normal distribution. Now, whether you compare for the Shapiro-Wilk test or Kolmogorov test, or you go for this Anderson-Darling test, right? So, conclusion is same here. Resolution time follows a normal distribution, right? And one more, that is the QQ plot, right? So, earlier we have already uh, plotted the QQ plot for batch wise, but if you want to compare for the whole data. If you want to compare for the whole data, we can have a QQ plot for entire data. So this is the QQ plot for all 15 observations together. Okay, so this shows that the data is normally distributed using graphical method as well as using the normality test, either Shapiro, Wilk, or Kolmogorov-Smirnov, or Anderson-Darling test. Okay, so these are the assumptions, right? Now, the equality of variance assumption is satisfied. Normality of the data, that assumption is satisfied, right? So now we can go for the analysis of variance technique, that is parametric analysis of variance technique, because data is normal. Okay, because data is normal. In Anderson-Darling test, p-value is less. Yeah, it is. It is 1 minute. Let me check. See, Anderson-Darling, it is okay. Okay. Anderson-Darling, it is not less than 5%, 0.46, right? But the reason is this Anderson-Darling test is not commonly used. There are some, as I already told you, there are certain limitations, and it is actually it is 0.46, right? It is 0.46, and which is not less than 0.05, right? It is greater than 0.05. We are not comparing at 0.5. We are comparing at 0.05, right? So look at this. We are comparing at 0.05, right? So 0.46, which is not less than 0.05. Okay. So in all the cases, okay, in all the cases, it is normally distributed, right? So this is a very, very important step, right? So your data is normally distributed. So we can go for uh, ANOVA test, right? Now in ANOVA, we have two tests. One is a Wells test, Wells F test, and another is a Fisher F test, right? So depending upon the equality of variance assumption, we have to choose the one. So that already I have explained you in the previous part, right? Because we have that Fisher's test. Look at this. So variances are equal. So we can use this part. Okay, we can go for this data, right? Fisher's F test value is 10.251. The degrees of freedom is, first degrees of freedom is 2, because I am comparing three groups. Degrees of freedom for error that is 12, because it is n minus k, 15 minus 3, so that is 12, and the p-value 0.00253. Okay, so this row we have to use. If variances are not equal, then we can go for well stated. But in our case, variances are equal, so we can go for that. Okay, we can go for the Fisher. Okay, so look at this. Because the variances are equal, we can go for Fisher's test, right? And this is the value of the test statistics. This is the value of the p-value. Okay, that is 0.00253. Right, now it is clear that the p-value of the Fisher's f-test is less than 5%. Okay, it is less than 5%. So we reject the null hypothesis. Okay, we reject the null hypothesis. So what is our null hypothesis? So it is all the means are equal. Mu1 equal to mu2 equal to mu3. Right, that is our null hypothesis. So that is rejected. Right, so okay, how homogeneity test, either we can check Leibniz or Bartlett. So basically, Bartlett test, Leibniz test, we can use Leibniz test also, we can use Bartlett test also, right? So there is no that much difference. These are the alternative tests. But Leibniz, instead of Leibniz, we can go for a Bartlett test because it is a parametric test, right? Leibniz, sometimes it is used in non-parametric section also, right? But you can use either of the two tests, right? So actually, because I have installed more tests, so it gives me Bartlett test. By default, it always gives you Leibniz test. Okay, so you can use any of the test. Okay. Okay, now this is how we can draw the conclusion from the ANOVA table, right? The p-value is 0.00253, which is less than 5%. So reject the null hypothesis about equality of mean. That means equal means hypothesis, mu1 equal to mu2 equal to mu3, that is rejected, right? So their means are not equal, or in other words, we can say that means are significantly different. Okay, now since means are significantly different, your null is rejected, then we have to go for post hoc comparison. Then we have to go for a post hoc comparison, right? So without that, that means post hoc comparison is applicable only if it is applicable only if the null is rejected, right? Otherwise, we have to go for we have to stop there. Okay, so the dissolution time for at least one pair of batches differ significantly. Okay, now which pair? The question is which two pair differ significantly, that we want to verify. Okay, so for that we have to go for the post hoc analysis. Remember, again I repeat, post hoc comparison is used only when the null hypothesis is rejected for the analysis of variance technique, right? If null is rejected, then only go for the post hoc comparison. If there is no difference, that means all the means are equal, so there is no need to compare, go for the pairwise comparison. Okay, now in Jamovi, it is already there, right? So look at this. If you look at this, so just scroll down. So just scroll down, and we can see at the bottom we have the post hoc test also, right? So these are the different post hoc comparisons, right? Now again, if the variances are equal, we go for Tucky's HSD. Tucky's on a significant difference. That means if the Fisher's F-test is used and the hypothesis is rejected, go for Tucky's pairwise comparison. If Welch ANOVA is used, go for Gem's Howell pairwise comparison. Okay, in our case, we have the features, so we can select the keys equal differences, right? The keys with equal variances, right? And then you can see at the bottom, we have the output. Okay, so this is the output for that. Okay, the keys post hoc test, right? Time is a variable. Batch 1, batch 2, batch 3, these are the labels. Okay, and we have mean difference and the p-value. See, along the rows, we have batch 1, batch 2, batch 3. Along the columns also, we have batch 1, batch 2, batch 3, right? So, all possible pair, batch 1 is compared with batch 2, 1 is compared with 3, 2 is compared with 3, right? So the remainings are obvious, and you can never compare 1 with 1, 2 with 2, 3 with 3 because they are equal. Okay, so these and the first row represents the mean difference. So what is mean difference? So batch 1 mean minus batch 2 mean, that is 0.58. Now look at this. In our summary, we have 20.333 minus 19.750. So this difference is this 0.58333, right? So mean difference, okay? And the second row represents the p-value, okay? Second row represents the p-value, okay? So it shows the p-value, okay? Again, we have one another option available, flag. See, by default, it is not giving you anything else. It gives you only the p-value. But whether it is significant or not, that user has to decide depending upon the p-value, right? But in Jamovi, we have the additional options, that is flag the significant comparison, right? Flag the significant comparison, right? See, once I have tick mark this option. So this batch 1, batch 3, it shows 2 star. Batch 2, batch 3, it shows single star. Now why this star? So look at the p-value for these. Okay, for 1 and 3, the p-value is 0.003, right? 0.003, which is less than 5%, right? That means there is a significant difference. Okay, there is a significant difference. Okay, same way, 2 and 3, the p-value is 0.01, 0.01, which is less than 5%, right? So this 1 star, 2 star, that is just to compare the p-value, whether to compare with 5% or 1% or 0.01%. Okay, but here these two differences, and it is obvious, right? So look at the difference, mean difference, 1 and 2, 0.58. So 0.58 difference is very small, right? 1 and 3, the mean difference is 8 point, which is large, right? And that can also be observed from this. Look at this. Batch 1, the mean is 20, and batch 3, the mean is 11, right? So average resolution time for batch 1 tablet is 20 minutes. Average resolution time for batch 3 tablet is 11 minutes. So there is a huge difference. Okay. So 1 and 3, there is a difference. 2 and 3, there is a difference. But 1 and 2, 20 and 19. So they are approximately equal. Okay. So 20 and 19. So this is how we can compare. Okay. So this is the output, right? And the comparison, right? You can use the flag, and these are, right? So this blue indicate that there is a significant difference, 1 and 3, then 2 and 3. And if you write the interpretation, so you can write like this. So mean resolution time differs significantly for batch 1 and batch 3, right? Batch 2 and batch 3, right? So 1 and 2 do not differ significantly. Okay, 1 and 2 do not differ significantly, right? So this is how we can use analysis of variance technique one-way ANOVA in Jamovi, right? Once the null hypothesis about one-way ANOVA is rejected, we can go for a pairwise comparison that is known as a post hoc analysis. Okay, that is known as a post hoc analysis. Okay, now this is just one another example for practice, right? So you can practice at home, right? Because it is good if you really want to learn. So just enter the data, okay, or create a data file. Now you know how to create a data file, right? So we have okay, just one important question. Can anyone tell me how many variables are there and which are the variable names? You can unmute yourself or you can drop a message in chat box. What are the variables in this example? Hello? Yes. Okay, there are two variables. Good. What are the two variables? Name of the two variables. Okay, two variable, that is great. Okay. So first variable is temperature. Second variable is density. Okay, good, good, good. Fine. Yes, yes. Now tell me which one is continuous and which one is continuous in the sense which one is a dependent variable and which one is independent variable. First tell me the independent variable. Independent variable. Okay, Shubhasri says density and Dr. Ananga says temperature. Yes. Uh, See, in this case, the density of the brick depends upon the temperature. Okay, density depends upon the temperature, right? So depending upon the temperature, the density changes, right? So temperature is your independent variable and density is your dependent variable. Temperature is a independent variable, density is a dependent variable. Very good. Now, how can you enter the data? Just one simple question. First column, either first or second column, right? So there are number of observations here. Look at this, there are number of observations. So density is a continuous variable, okay, and temperature. So actually it shows 100, 125, 150, 175, but we can call it, we can label them temperature 1 or temperature 100, temperature 125, temperature 150, temperature 175. So there are four labels. Okay. So that can be taken as a categorical variable or say ordinal variable or nominal variable. It's a categorical in short. Okay. And density, it is a continuous variable, right? So just practice on this, right? Once you practice, you will realize what are the difficulties. Okay. But and already in my presentation, almost all the steps are mentioned. Okay. How to enter the data. Okay. So see how many variables are there, Kanchana? There are two variables. Okay. There are two variables. So you have to create two columns. Either you can create in Microsoft Excel or you can create in as a CSV file or directly you can enter. Say for example, my first column is density. So just go on entering the values 21.8, second value 21.9, 21.7 and so on, right? Once the 100-degree temperature data is over, you can continue with 21.7, 21.4 and so on, right? And then that is your first column. Okay, that is your first column. What is the second column? The second column is the temperature. Okay, second column is a temperature. So you can create another variable and call it, give the name temperature, right? And then in that case, you can write 100, 125, right? So for first row, right? See, for all these 21.8 to 21.8, this row, you can give the value second column as temperature 100, temperature 100, and so on. Or you can simply say 1, 2, 3, 4, and give the label 1 for 100 degree, 100 degree Fahrenheit to 125 degree Fahrenheit for 2, right? So it depends, right? But you have to enter the data in two columns. Okay, first column is density, second column is temperature, and the number of rows. So it is 1, 2, 3, 4, 5, 6, 7, 28, and 1, 3, 4, 5, 6. So just 22 observations, 22 rows are there. Okay, so I think it is clear how to enter the data. Okay, or you can see my earlier data file. Okay, so depending upon that, dependent variable, independent variable, that's it. Okay, so this is how we can enter the data. Okay. Okay, good. Okay, now this is about the practice example. So you can practice it, you can enter the data on your by your own, and just follow the presentation, check the assumptions, explore the data, check the assumptions, and then carry out the analysis of variance. Then depending upon the equality of variances, depending upon the normality, right, you have to choose appropriate p-value from the output, and then you have to draw the conclusion. Okay, so this is about the one-way ANOVA, right? Now, suppose your data is not normally distributed. We have more than two groups to compare, but the data is not normally distributed. Okay, data is not normally distributed. So obviously, like in t-test, when the data is not normal, independent t-test, when the data is not normal, we have the Mann-Whitney u-test. That is non-parametric test. Okay, so exactly same way, when the for ANOVA type data, if the data is not normal for one-way ANOVA, we can go for, if it is not normal, we can go for the Kruskal-Wallis test, right? So it is again, it is an extension of Mann-Whitney test when more than two populations are to be compared. Okay, it is a non-parametric alternative to the analysis of variance technique, right? Recommended when the assumptions of ANOVA are not satisfied about the normality. Okay, so for this Kruskal-Wallis also we have the assumptions, but these assumptions are very, what would you call it, as a moderate assumption, right? The K samples are independent, that is common. The observations, the sample must be selected independently. The sample is a random sample. You should always select a sample randomly so that to reduce the bias in the selection, right? Variables have a continuous distribution. Now, there is no strong assumption about the normality or any kind of distribution. Just it is a continuous, it has a continuous distribution. Populations have same variabilities and populations have same shape. These are the assumptions, right? Hypothesis, usually in the parametric test, we compare population means mu1 equal to mu2 equal to mu3. In non-parametric test, generally we compare the distribution functions or we compare the population medians, right? So instead of comparing means, we compare medians, right? Now, last time also I have explained you why we use median in non-parametric. The reason is median is least affected by the extreme values when your data is not symmetric. So median is less affected. Okay, so all the medians are equal against at least two medians are different, right? So this is the assumption. This is the test statistics, right? Kruskal-Wallis test statistics. So generally Kruskal-Wallis test or any non-parametric test, it is based upon the rankings of the data. Okay, so we arrange the data and rank accordingly, right? And we can have this formula, and using that formula we will get a Kruskal-Wallis test, that is chi-square test statistic H, right? And then we can compare the p-value of the output and we can draw the conclusion. Okay, so this is one simple example which I have taken, that is to detect the presence of harmful insects in farm field, we can put up a board covered with a sticky material, right? So to protect the field from the insect, harmful insect, we can put up a board covered with a sticky material, right? So that the insects stick on that particular board, right? And then the insect trap on the board, they are counted, right? But the idea is different type of colors are used for the boards. Okay, which color attract the insects? So on one board, a lemon yellow color is used. On another board, white color, green color, and blue color, right? And a sticky material is used, right? So depending upon the colors, the number of insect trapped on that particular board are counted. Okay, so this is about the number of insect, number of cereal leaf beetles trapped. These are the insect, right? So this is the data, right? And we want to uh, test the hypothesis about whether there is a significant difference among the colors with respect to the number of insect trapped. Okay, so this is the example, right? Now, uh, in this case, again, we have the data file, that is insect trap XLS data file. If we open the data file, we can see that there are two variables. One is the insects, that is continuous, and another is a color, that is categorical, right? But here by default it opens it consider insect as a categorical, so we can change that as a continuous, right? And then just modify the data, explore the data, that is exploratory analysis. Again, it is exactly same which we have used earlier, right? So we have this is the number of insects, right? That is continuous variable, color, and we have the summary statistics, right? Then we can go for the mean, median, mode, you can check, right? You can go for the plots also, right? These are the plots, right? And then set up the hypothesis. Since we have four colors are used on the board, so we have the hypothesis that the median number of insects trapped with respect to colors, there is no difference. So mu1 equal to mu2 equal to mu3 equal to mu4, or at least two median differ significantly, right? Now, if you look at this, so let me show you that. Just open the data file, open, then the browse, and it is insect trapped. Okay, so this is the data file. Okay, so just change this to continuous. Remaining part is as it is. You can go for the descriptive summary, right? Already I have explained you, right? So select the insect as a continuous variable, color as a splitting variable, right? And then you can go for the statistics, right? Depending upon our requirement, we can use different statistics, right? You can choose the Shapiro-Wilk test also here. So look at this Shapiro-Wilk test, right? So actually for this data, it is normally distributed, because if you look at the p-value, all the p-values are less than are not less than 5%. So it is normally, but we can use it for the just for the comparison, right? So this is how we can use. Then you can go for the plots also, right? We can use a box plot. So these are the box plots. So look at this. At some places we have the outliers also. See, in the third case, we have there are two outliers, right? And you can see the box plot. Okay, at the same time you can have a histogram also, or density plot also, right? So these are the histograms, histogram or density plot. Because we have limited number of observations, so histogram is not that much useful, but we can have a density plot. Okay, and then go for the ANOVA. You can go for the analysis of variance and non-parametric, that is Kruskal-Wallis test. Okay, so here simply select the variable, continuous variable, dependent, then grouping variable, and we have the output, that is a chi-square value, the degrees of freedom, and the p-value. Okay, so if you look at the output, so we have the chi-square value, the p-value is 0.0071. Okay, it is 0.00071, which is less than 5%. So reject the null hypothesis. That means at least two medians differ significantly. Okay, at least two median differ significantly, right? So this is how we can have. Here we can also compare the effect size. So there is one more option in the Kruskal-Wallis option, that is effect size. So it gives you the effect size also, that is epsilon square, or we in the theory we call it as eta. Okay, 0.73. So look at this eta square. So this is the value, right? And depending upon the value of eta square, we can draw the appropriate conclusion. If it is less than 0.06, there is a small effect. Okay, how to know whether to consider mean or median to compare. Okay, so as I told you, usually for the parametric test, we always compare mean, right? The reason is in parametric test, normality assumption is required, right? And normality means a bell-shaped curve. In that case, mean and median, they coincide, right? So generally we use mean, right? But when the data is not symmetric, when the data is not a bell shape, it is either positively skewed or negatively skewed. So in that case, mean is not suitable measure. That means if the data is not normal, mean is not suitable. Okay, so in that case, for the non-parametric, we can use median for the comparison. Okay, we can use median for the comparison. In this example, particularly, right? Actually, normality is satisfied, but still I am using a Kruskal-Wallis test just to show you how we can compare. Okay, but if normality is not satisfied, and then always we have to use median for the comparison. That means for this example, for this uh, what we call, it is about the uh, that Beatles examples, right? So we can apply the one way ANOVA also. Okay, so this is how we can compare, right? So this is about the eta square, right? And then since in this case, if you look at the output, okay, the p value, it is rejected. So here also we need to apply the pairwise comparison, right? Because null is rejected, that means there is a difference, right? At least two median differ significantly out of four. So that I want to know which particular two color differ significantly with respect to the number of median number of insect trapped. Okay, so in Jamovi, we have the option, right? So in Jamovi, 1 minute, we have the option, and that option is this DSCF pairwise comparison. Okay, so look at this. This is the DSCF pairwise comparison. So DOS, Steele, Critchlow, Flinger pairwise comparison, post hoc analysis, right? And here it gives you all possible pairs, their test statistics, and the corresponding p-value. So if you look at this, say for example, this blue and lemon yellow, it shows the p-value is 0.02, which is less than 5%, right? Similarly, lemon yellow and white, it shows 0.02, which is less than 5%, right? All the other remaining, they are not less than 5%. Okay, so this is how we can compare More than that means we can compare pairwise in the critical values. Okay, so this is the pairwise comparison, right? And we can see that blue and white color, right? And lemon yellow and white color, so that differ significantly. Okay, so this is all about the uh, pairwise comparison in critical values test, right? Now, many times what happens? So we have the data like this, right? See, in this case, what I have the data like this. A drug company is interested in testing three forms of a pain relief medicine, right? Three forms of a pain relief medicine. 27 volunteers, sorry, were selected and 9 were randomly assigned to one of the three drugs. Okay, and the outcomes are the rating scale, pain report on a scale, pain on a scale of 1 to 10. So 10 is the most pain. Okay, so 10 is the most pain, and 1 or 2 or 3 they are mild pain. So the responses are in terms of 1, 2, 3 up to 10, right? So when we have this type of data, right, and we want to compare, right, when we have this type of data, look at this: drug A, drug B, drug C. Using drug A, right, so this is the leveling scale of 1 to 10, right, and you want to compare, right? So actually the outcome or the output, this variable observation, is on the rating scale, right? So when your data is ordinal, right, when the data is ordinal, obviously we can go for the critical values test, right? So this is for the practice. So you just apply the critical values test on this particular data, right? And for more examples, you can go for this Douglas C. Montgomery book, which is very good book for the analysis of variance. Another one is this is Introduction to Practice of Statistics. Another one is Behavioral Sciences, Fundamental of Statistics for Behavioral Sciences, right? So this is all about today's session. If you have any questions, you can ask me now. You can unmute yourself or you can drop a message in chat box. Thank you, Bhagya Lakshmi. Thank you for the appreciation. Actually, Jamovi is very useful. It requires to practice. Almost every kind of statistical analysis we can perform in Jamovi. Even for the structural equation modeling, meta-analysis, meta-analysis. So all comparative to SPSS, it is very useful, right? So any questions? Thank you very much. Okay, two-way ANOVA. So when the data is classified with respect to two criteria. Okay, so two criteria. What is two criteria? So like in our example, the entire resolution time data is classified with respect to only one criteria, that is type of batch, batch 1, batch 2, batch 3. Okay, so that is why it is uh, one way ANOVA, right? So, but if we have, let me show you a simple example so that you get a clarity. Just 1 minute. So that you get idea when to use what kind of data you should. use for the two-way ANOVA, right? So this is for the two-way ANOVA. So look at this. Now this is the data, right? So in this example, all these numbers 124.1. So this is the dependent variable mileage. Okay, that mileage depends upon the type of gasoline, right? And the mileage also depends upon the type of additive, right? So these 9 observations are classified with respect to 2 criteria. One is type of gasoline, another is type of additive. Okay, so that is why we use in such a situation we can go for the two-way ANOVA. Okay, why find out effect size, sir? Which time based means what? I don't understand. Effect size is just for the comparison, how much effect is there. For that purpose, we can use. Okay, which time based means what? Okay, relationship between weight and hemoglobin of a children. What I know. Okay, which awareness hemoglobin of a children with awareness level. Actually, you are using two continuous variable. You are using two continuous variable. One is a weight, another is and hemoglobin of a children, right? So two continuous variable, and you are mixing with hemoglobin of children with awareness level, right? So this awareness level, so I need to understand your data first, right? Academic performance is dependent on both on ICT intervention and self motivation. So you can categorize this ICT intervention into different levels, self motivation or not. We can do that, right? Okay, so you can go for one way ANOVA. Okay, and significant or not significant. So actually, when we say that there is a significant difference, Ilango, right? So effect size is used how much significant difference, right? So if you look at the last slide, right? When we have calculated eta square, so in that case we can go for that. You can compare from that how much effectivity. Okay. Okay. Thank you very much. Uh, it is one way ANOVA, right? Subhasri, it is one way ANOVA, but since the data is ordinal rating scale, so instead of applying ANOVA, we can go for the non-parametric, that is Kruskal-Wallis. Okay, we can go for a Kruskal-Wallis. Okay, and, Kiran Kumar, Mundapatti, Kiran Kumar. Thank you very much. Thank you very much. Okay.
You can, sir, excuse me, you can unmute yourself and speak if you have any
Yeah,
doubt.
you can unmute yourself also.
So today is the last session. Tomorrow we'll be having Paraksha share session.
Even you have my email address on my presentation on the first slide. I have mentioned my email address. If you have any query, you can drop a mail. So whenever I get a time, I will check and reply you in your uh, accordingly, right? So thank you. Okay, thank you, madam.
Yes, sir. Thank you, sir. Thank you very much, sir. Really, Jamovi was very interesting. Everyone felt very easy, I hope, when compared to SPSS. Still, there are some confusions in learning Jamovi. Uh, we think this program will reach everyone. They're asking for email ID again,
Yeah,
sir.
yeah, yeah, yeah. I am entering. Okay. So Raju0469 @gmail.com. Okay, thank you very much.
Sir, thank you very much, sir. We extend our heartfelt appreciation for your invaluable guidance and expertise on this topic, analysis of variance. You have inspired us to explore the nuances of ANOVA with enthusiasm and curiosity. Thank you very much, sir. Your dedication in fostering our learning and empowering us with statistical insights has left a long-lasting impact on our research activities. Surely we will be implementing everything in our research work. We are deeply grateful for your unwavering support and guidance, which have undoubtedly enhanced our analytical skills and broadened our perspectives in data analysis. Thank you very much, sir, for introducing this company.
Huh? Hello, ma'am.
Madam,
Yes,
Ma'am, I
ma'am.
have one question. Ma'am, hello, sir. Sir, this
Madam.
Jamovi, online Jamovi, when we open it on the website, it is only 1 hour, sir, it will be active. Only 1 hour
Yeah,
it will be
yeah,
active.
yeah, yeah. The problem is
Okay, sir.
that is available only for 45 to 50 minutes only, I think.
Okay, sir.
Limited version.
So,
Limited version.
sir, we can download like SPSS, we can download the results from Jamovi, sir. Or
Obviously,
we
you
can
can
copy and paste it. Or like
you
SPSS,
can,
we can.
yes, yes.
Or how do we take the data, sir, after the analysis? Like SPSS, we can take the results from there. But
Here
here Jamovi,
also,
we can take the results, sir. Graph and all, we can take it into the.
everything you can copy and paste in Word or Excel, whatever. Okay.
Okay,
And
sir.
even whatever the report you get, that can be printed as a PDF file, or that
Okay.
can be copied into Word also, right? And Jamovi is open source, so anytime you can download it, install it in your laptop or desktop, right? And you can use it anywhere because it is open source.
Okay,
Okay.
sir. But that's SPSS, we have that save file. That one, whenever we open it, we have all our data there. And I mean, the data variable sheet,
Here,
everything is there. But here also,
here
we will have
also,
it, sir. We will have it.
obviously, here also we have the data file, we have the output as well. Remember, in
Okay.
SPSS, you have two separate files. One is a data file, another is the output file. Okay. So two separate files you have to maintain. Here we have data file. When you open the data, carry out the analysis, and at the end, when you save that, so your data as well as your analysis will be saved in a single file. And next time when you open, so same data along with the complete analysis.
Okay, sir. Thank you, sir. Thank you very much.
Thank you. Thank
Thank
you.
you very much.
So already I have shared the presentation, earlier presentation. So this
yes,
presentation
everything,
also I will share. Okay.
everything you have sent to mail, sir.
Okay. Then that Mandapatti is asking for the presentation. Okay, I will share this presentation along with the data file.
Yes, sir.
Okay. Not for the practice, so that you can practice yourself. Okay.
Yes, sir.
Okay. Thank you very much.
Thank you very much, sir. It was really very nice working with Jamovi. Thank you very much, sir. We'll meet in the
Okay.
next program, sir. Okay.
Yeah, sure.
Thank
Okay,
you, sir.
good night all.
Good night,
Good
sir.
night.